Many of you are wondering, how can I tell what will happen? Well, here's the explanation we give in Chemistry 1220. Best I can say for you is there are three factors. The first one is bond polarization, the second one is bond strength, and the third is conjugate acid-base stability. All right, that's really the best I can do. If I move on to the next slide to become more detailed, you know bond polarization is where we put a partial positive, partial negative on the atoms in a bond. So something like acetic acid, when it's in water, will release H+. Here, the hydrogen is partially positive. Here, the chlorine is partially negative. But we could also have a reverse polarization. We know sodium cations are always positive. In this case, the hydrogen is partially negative. It is called a hydride. We don't talk too much about it in this class, but again, it is a way a chemist uses to see what's going to be going on. Then we could just have no polarization whatsoever. Those are molecules like methane, ethane, things like that. They do not readily give up a hydrogen. So remember, we're talking about giving up a hydrogen. That's really what it is. So that's bond polarization. The second is bond strength. And the overriding factor is if I have a strong bond, it will dissociate less. So what I have here is a series of bonds to hydrogen where I've looked at the halogens. Even though HF has the largest electronegativity difference, its bond strength is going to override polarity. It wants to hold on to that hydrogen, and it is a weak acid. The last one is the conjugate base stability. Go back and look at the tables that have the actual values for KBs. The greater the stability of the conjugate base, the stronger will be the acid. So I'm just going to use HCl. This is a very strong acid, 100% H plus Cl minus. There is no back reaction. So the Cl minus is an extremely strong conjugate base. It is not going to, it's a very stable conjugate base. It is not going to have a back reaction. So it's like a potpourri section here, a little bit of everything. When we talk about binary acids and hydrides, we mean one element bonded in some way to hydrogen. There can be more than one, but we just have two different elements. Notice what happens. In group 4A, we don't have acid or base properties. In group 5A, each of these hydrides are weak. We have our neutral water, just like the first one was neutral. Then what we have are a series of weak acids. It is factual, it is observation, it is measured. And then we have our HCl and our HBr that are both strong acids. So again, all of this is factual based on observation. And since you see the Ks, you know there are also measurements. Another type of material that's in this section is called an oxyacid. Here is the oxy part, there is the acid part. Two different cases. Sometimes we have the same number of oxygens. I'm just going to hop down here and kind of put a little circle. Notice how there are the same number of oxygens, and what we will see is the acid strength will increase with increasing electronegativity of the central ion. Here at the chloride, we have an electronegativity of 3. Our K is 10 to the minus 8. Here, it drops down to a 2.1, and our acid dissociation constant becomes very, very small. Take some time. These are the facts. They're not going to change, again, based on observations because we have equilibrium constants. Another type of oxyacid, it has more oxygens. And a good way to look at this is to look at their Lewis structures, which are placed here. The red hydrogen is the hydrogen that is going to be given off in terms of the acid-base reaction. What I like to tell students is there is some polarization here. Here, because we have an extra oxygen, there's more polarization. Here we have 2 oxygens. There's even more polarization. Here we have 3 oxygens with the chloride. There's even more polarization. So when you were forced to memorize all the way back in 1210, we said the chloric and perchloric acids were the strong acids. We then said hypochlorous and chlorous are the weak acids. Now that you've learned about equilibrium constants, you can see that hypochlorous and chlorous have equilibriums that lie to the left on the reactant side. Again, factual. You are going into different fields and you're going to run into carboxylic acids. Anybody that's taking organic chemistry is going to have this happen to them. Carboxylic acids, let's use as our poster child acetic acid, and let's say it has an equilibrium constant on the order of 10 to the minus 5. What if I replace each of those hydrogens with the more electronegative fluorine? Well, when you go into the literature and you look for the value, you can see that the equilibrium Ka has become much larger. That is because the fluorines are more electronegative. They are pulling, allowing for the release of the H+. So when I look at this, I say I'm using these symbols, but symbols are what we use to represent the facts in chemistry. Another thing that appeared in Chemistry 1210, and it really should not have appeared there because it talks about electron dissociation, electron delocalization. If I have a negative sign on a carboxylic acid anion, those electrons can undergo a process called resonance, and we can put the charge on the other oxygen. More with organic chemistry, I rarely talked about this because I felt it was kind of past where we were in Chemistry 12. So what you're also going to run into in your careers, and they're in our bodies right now, are the amino acids. We've got 2 different things there. We've got a carboxylic acid group and we have an amine base group. Which of these is going to quote unquote win? Will this act as an acid or a base? The other thing that can happen is we can form Zwitter ions where we can transfer this proton from the OH to the nitrogen that has the lone pair. So this again is the neutral molecule, but when we transfer the electron, it is going to be, when we transfer the proton, it is going to be a Zwitter ion. Again, this will not be on your exam. I'm just doing it to show you where what we're doing fits into your overall education plan. There are 20 amino acids. You're going to cover them in your other coursework, and you'll learn about what they do, why they're required, what their functions are, what about a deficiency. I just want you to see them, all their different structures. And I'm not going to do this one here. I most likely will do it in class, but it's an integrative exercise. Our class, even though it's arranged in chapters, that's not how you use it in the real world. You use your knowledge base to solve whatever problem is presented. I come from industry. I did not focus on one specific thing in industry. You're kind of not allowed to do that. Whatever it is they want you to work on, you work on, so you use whatever knowledge you have. Same thing in whatever profession you use. You're going to use all these little bits and pieces from the torturous general chemistry class in order to perform in your career.